All right. Hey, everybody. So today, this is our second office hour, and the main thing I want to talk about is what happens when you do decide to scale. Mainly, I'm going to talk about log transform, but same logic applies to any other kind of scaling that you do. But basically, what that means, how do you interpret your model output then, and then also when applicable, when do you have to change your metrics? All right, so to start, and this notebook's already run just so the numbers are consistent. So here we're just importing our usual stuff, and we're going to start with a baseline model. So we're going to use our trusty miles per gallon data set, and this is the function that I took from last time. And then what I'm doing, I'm just renaming some column names. Something to note is as you're working on your project, stats models, where you have, your formula being in this format, be very careful about column names because sometimes that might throw it off. So underscores are okay, dashes are not okay, periods are also not okay. I know that in the housing data set, there are some column names that have, or if you, for example, create dummy variables out of like the number of bathrooms, I think there's like 2.5, 2.75 that will actually throw it off. So be very careful about that. If you have any like symbols in any of your columns and you're finding that your stats models isn't working because even though it should, that's probably why. And the reason for that is because this formula is written in R syntax, and in R syntax, some symbols have different meanings. So if you run into like a period problem, or like, I think if you even put like a percentage sign, it actually will not work. So just in case y'all run into any of that. Okay, so I'm changing a couple of the column names because spaces also don't work. So before here, data had a column called model name, I think, or model year, and I just switched it such that is the singular word. All right, so to start, let's do a baseline model. Here I'm only picking the four, I'm just picking these four X variables just because there's just one that's very, very insignificant. We'll see how we can help that a little bit. All right, so this is a baseline model run on these four X values. I do my train test split, throw it through my modeling function, and you can see my R squared on the train is 0.82, on the test is 0.77. So about like a 5 percentage points of difference between the two R squared, and the RMSE is roughly the same as well, closer to 3 on the train, closer to 4 on the test. Something I want to double check real quick is let's take a look at the distribution of our Y variable. So I think it's Y dot plot, and then kind is histogram. Is that right? Okay, cool. So this is our miles per gallon. Actually, let me just rerun this quick. Okay, so Y is our miles per gallon. And as you can see, it ranges from around under 10 to 45. And we have an overall root mean squared error of about 3 to 4. So that's actually not so bad, I think. I don't know in the context of cars, but if the miles per gallon can range from 10 to 45 and I'm getting an RMSE about 3 to 4, I think that's okay. That's like maybe like a 10% of the entire range. So maybe not so bad, but maybe we can do a little bit better. So let's see. So I ran this as a baseline model. Let's take a look at some of the distribution in the between these features and the target. So here I have a bunch of scatter plots, basically every X that I'm using against the Y. And this is the kind of ED that you should be doing for checking for linearity, especially, as well as multicollinearity, but linearity for now. As you can see, weight seems to be like, okay, this one looks like there's a pretty strong linear looking relationship here. Acceleration a little bit less. Year, you can see that, yes, it is kind of increasing with the years, and origin kind of as well. To start, let's start with something easier. Let's start with weight, and let's see what a transformation on weight can do. So what we're going to do is a log transform. And when I log transform weight, I actually have a graph over here. The log transform version of weight looks like this. So this, you can see, is a lot straighter compared to this. And the reason for that is what a log transform does is anything on the lower ends are going to be spread out a little bit more, and anything on the high ends are going to be squished together. So where you usually have, like, if you're seeing that you have a more of a curved relationship between two variables, a log transform typically does help it become more linear. So you can see here, this is what we had before for weight, more of like a slope curve down. And then when we log transform it, it looks a little straighter, a little bit more linear. Something else to note is that the scale of weight changes. So whereas weight here ranges from like 1,500 to about 5,000, that's our range of weight. Our range of log weight is a lot smaller. Our range of log weight is 7.4 to 8.6. So same numbers, just log transformed. The scale changes quite drastically. So how do we then interpret coefficients that way? So to log transform weight, all I'm doing, and this is not the best way to do it, but of course, in your code, you will do it better. What I'm doing is I'm just replacing the weight column with the log version of itself. I think the safer way to go about it is probably either make a new data frame or a new column. Here, I'm just replacing it, which is not the best thing to do, but works for now. So when I have this, I train test it and I run my model again, you'll see that my metrics do better. My train and test R squared are at 0.83 and 0.86, up from 82 and 77. And my RMSE, where it was before 3.2 and 3.8, we've done a little bit better. We're at 3.1 and 2.7. I think this might be one of the cases where the train set has a lot more outliers, which is why we're seeing better test metrics than train metrics. But let's just rerun our train test and we'll see that our RMSE tends to pretty consistently do a little bit better. So keep running this. You see this maxes out at like 3.4. This is not a good practice, but just to show that, you know, one, sensitivity in the train set, but also overall the results are just a little bit better. So you can see that our R squared for our stats models shows a 0.845 compared to 0.827. So we've done about 2% better just by log transforming weight, which already looked to have like a pretty linear relationship. But this just goes to show that the more linear the relationship, the stronger model fit you'll get. Just because you're trying to fit a straight line, it makes sense that you want to fit a straight line through straighter looking data. Questions about anything I've just mentioned?
Yeah, so correct me if I'm not saying this right, but what you're saying is when we log transform, we should create a new column based
Yes.
on the original column.
Yeah. For me, it's lazy coding, but for you, you might want to do something like log weight equals to numpy log x weight. And then when you train test split, or before you do this part, I guess you would then look at x here. You see I have my log weight here. I would maybe for x, drop the regular weight and then do your train test split then. So just so you don't overwrite, well, in this case, mine is overwritten, but oh wait, it's not, but never mind. Yeah, it's better to just make a new column rather than replace your original values, because it does get kind of confusing, especially if you're doing a lot of different transformations.
And I'm curious what the conversion from weight to log weight, like what is that? How it's that converted?
Yeah, so it's the log distribution. So log distribution basically is, let's see, how do I, actually, let me just Google that. Log distribution. This is a, let's see, let's see what images we can find. There we go. Okay, so this is a log distribution. This one on the right here. So this is what a log curve looks like. And so for any value of x, you can get log of x. And it's sort of shaped like this, that like kind of plateaus out. And that's what helps it stretch out the beginning values and squeeze together any outlier or extreme high values. It's what it's doing is it's not like a direct conversion, but it's just a log formula. I guess if you want like the specific formulas, these are it. But yeah, people just know it as like a log transform.
All right.
Yeah, so actually we can really quickly take a look at what happened to weight. So if we take a look at, let's see, data weight, and we plot it. So this is what weight looked like before. And then now, if we want to look at log weight, I think we have to do, I think I saved on X, log weight. Log weight now looks like this. So you can see that where it was a little bit more skewed before you log transform it, after you log transform it, it becomes a little bit more symmetrical. So that's sort of like the idea of a log.
So you would advise like to do that for our project, like to make sure it's tight and like, you know, I guess more, if it's lower spread out, make it more spread out. And
Yeah, I would say it's one of the things that you can try. In a little bit, I'm going to talk about like what that means in terms of interpreting your results, which is why any sort of transformation just makes your model a little bit harder to interpret, and I'll talk about that in a little bit. But yes, you typically, if your goal is to have like a high R squared and like a better fit, log transform usually does help.
all right. Thank you.
You're welcome. Okay, so any other questions before I move on? All right, because I'm going to talk about interpreting the coefficients now. So this, based on these two metrics, consistently better than what we had before, and we only log transformed our weight variable. Now, here, our coefficient that we had for weight previously was 0.006. So every increase in one, I'm guessing pound, of this car will lower its miles per gallon by 0.006. So this is the kind of scale that we were looking at before. But now, looking at this, we have a coefficient of -18. So every time you have one increase in the log of your weight, your miles per gallon will go down by 0.18. Now that, as you can see, is already like a layer of decoding that you would have to do. Like, what is one increase in unit of a log weight, right? That's a little bit harder to interpret. Now you can either reverse log this number by taking an exponent. I believe all you have to do is take an exponent of, I hope this is right, 18.558. If not, I think it's 1 over. Let me just check real quick. I think this might be it, but I forget. Another way you can do that without going into the math of undoing the coefficient transform is, I linked this article over here in our guidelines in interpreting when you log transform any variable. And here it shows you the difference between when you log transform your y, log transform your x, and if you log transform both. And this is just a different way to interpret. Oh yeah, okay, so you can see that this is the, oops, not this one. This one is how you untransform it. So basically, when you have a log weight variable, you can say that if we increase the weight by 1%, we expect y, our miles per gallon, to increase by beta divided by 100 units of y. So what that means is, instead of looking at it as like an absolute increase, where before we could say, all right, it'll go down by -0.006, here we can say that it goes down by 0.185 miles per gallon for every 1% increase in the weight. Let me just copy and paste this over here so we'll have this. So if we increase x by 1%, we expect y to increase by that number of units. Let me move the markdown. Oops. There we go. Okay. So therefore, with this, if we increase weight by 1%, y will increase by or decrease by 0.185. That's another way that you can interpret this log variable. Questions on this? All right. Next, sometimes it's just more efficient to transform your target variable, which ends up being a lot more destructive in terms of how much interpretation or change in interpretation you'll have to do, but sometimes you get better results through that. So one way you can check to see if you should transform your dependent variable or not, these are just scatter plots of log, actually I should put logged miles per gallon because you can see I'm taking the NumPy log of the y value, and the relationship between all of these look a little straighter. This is logged miles per gallon, logged weight. And you can see that's a great relationship there. But yeah, based on this, sometimes it's just more efficient to log your target variable because it straightens out the relationship between the target and every other variable that you have. And so how do you then interpret coefficients that way? But first, let's take a look at our metrics. So this is just me rerunning everything, but just logging miles per gallon. I even re-imported the CSV, so it's definitely clean. So when I rerun this, you can see that our R squared is a lot better, right? It's a 0.87 compared to, I think we never broke, oh, I guess 0.87, this is 0.84. So it's a little bit better. I think if we just rerun it a couple times, pretty consistently at the 0.87, 0.88 almost range. The one thing that some people get deceived by is your RMSE. So here, our RMSE is very, very low. Like before we were looking at roughly like 3 to 4 miles per gallon of error of RMSE, but here we're looking at 0.1 or 0.13 train and test RMSE, which is a lot smaller, which some people think, oh, great, very low RMSE, that's awesome. But remember that what we're doing is we're predicting the log of miles per gallon, not miles per gallon itself. So we take a look at what happens when we transform miles per gallon. Let's see, this is our Y, and then we have our data miles per gallon. Okay, so we have data miles per gallon. Let's just plot a histogram of that. This kind equals this, and this is our miles per gallon. Now our log miles per gallon, and let me see, actually I can just do the log there. NP log, there we go. Now we logged our miles per gallon. Here you can see that the skew kind of like, it gets more symmetrical basically, but the scale of miles per gallon is completely different now. We went from a scale of around 10 through 45 to about like 2.25 to 3.75. You can actually also see this in our scatter plots, like the range of miles per gallon is 2.25 to 3.75. Whereas before in our scatter plots, we had 10 through 45. So the number that we're getting for log miles per gallon are already a lot smaller. If we're just looking at this scale of like 2.25 to 3.75, an error of 0.1 is going to be relative to that scale. So therefore, this RMSE, this train and test RMSE, it needs another level of interpretation, right? Like this 0.1 error is saying that there's a 0.1 error in the log of miles per gallon, which for some people are like, okay, so what does that mean in actual miles per gallon? So that's what we have to do to unscale, figure out what the actual RMSE is. And with the function that I defined before, you actually don't have that embedded in the function. So you might have to tweak, if you do choose to write a function, you might have to tweak it a little bit to account for log transform variables. And I've seen this done a couple ways. I've seen this done as like you have a additional argument in your function here, an additional argument here to say whether the log is true or false, and you can undo it there, or maybe you write a couple different functions based on how you're scaling your data. But anyways, to unscale it, this is how we do it. You basically have to take the exponent because the opposite of log is an exponent. So where we had our predictions, so let's try to grab these predictions out. Okay, so these predictions will be all in like the 2, 3 range, which makes sense when your miles per gallon is in this range, right? Having your predictions be in like the 2 to 3 range, that makes sense. But that's not in actual miles per gallon. So therefore, we have to take the exponent, which is numpy.exponent of the whole thing. And these values have jumped back up to the range that we expect. And you can see there's like, I don't know, from like 15 to 30, which is within this range. So therefore, we have to do this untransform before calculating mean squared error to get accurate metrics. So what I'm doing here is I'm fitting my linear regression on my train set. I am then untransforming my predictions. And then here you can see I'm also untransforming the sets that I have fit it on so that they're all in the same scale. And then my RMSE is back to the 2 or 3 or 4 range. So as you can see from this model, the root mean squared error is actually around 3. Whereas I think before, where we only had this one was a little bit, this was above 3, where the train set was a little bit below 3. And so if you are doing a log transform, especially if you're doing a log transform on your target variable, don't forget to untransform it so that your error values make sense and match up with, and basically they, will match up with the scale of whatever it is that you're trying to predict. Cool. Any questions about this?
So that's only in the case that you do it on your dependent variable. You wouldn't do that you wouldn't like unscale before you do the RMSE
Of the other one.
Yeah, with the independent variable, right? That you would, okay.
Yeah, that's right. Because let me find it. Because for this one, we are using the log of weight to still predict regular miles per gallon. So your outputs here, and let me just rerun. Actually, I don't know if I can rerun this, but yeah, basically the outputs here, when you do a dot predict, will be the actual miles per gallon value. So therefore, our RMSE is still not skeptically low.
Okay.
Cool. Any other questions? All right. I will say that this is one of the things that for my other class, like we didn't really have time to talk about this. So a lot of people were getting like 0.0 something errors on like housing prices. And it was like, that's very, 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 very accurate for predicting the price of a house. So if you feel like your errors are a little too low, make sure you're not doing something like this. All right. That's the main thing I wanted to talk about for today. Do y'all have any questions? And I can stop the recording and we can talk more freely about our projects as well. All right, I'm going to stop here.